in 9.2, it says that we have a 4-kilogram mess kit sliding on a frictionless surface, explodes into 2 pieces, each having a mass of 2 kilograms. One is moving 3 meters per second in the north direction. The other one is moving 5 meters a second, 30 degrees north of east. And then it says, physically explain what direction the original particle comes from and what is the initial original velocity of the mess kit here. So what we want to do here is that we want to go in and start to look at this stuff here. So here we go. So the first thing that I want to do here is I want to draw a coordinate system. I know that each of these masses have the same mass. So when I'm looking at this here, the first thing that I want to do is that I want to define my system. And the way I'm going to define my system is that I'm going to call them blocks 1 and 2. And so when I look at this thing here, I'm going to set up my coordinate system, and let's look at my coordinate system. Well, they say north, which is of course our y, and then of course east is our x. Now, one of the things that we're seeing here is that we say that there's one block, let's say it's my red block, right? So when I look at my red block, it's going to be moving in this direction here. And I'm going to call this block number 1. And typically I would put a little 1 right here. And then I have a second block. Now the second block here, let's be careful here. So through the middle, this is our 45-degree angle. It's saying 30 degrees. So I'm going to assume that it's got to be less. So it's going to be moving in this direction here. So then my second block is moving in this direction. And this is moving at 5 meters per second. And I know this is small, but I'll draw it bigger a little bit later. And that's block number 2. And they're telling us that this is 30 degrees. It's north of east. So then I said that my system is block 1 and 2. Here I go. There's my system. So when I look at my system, what do I know about it? So, are there any external forces? And the answer is no. There was an internal force. Breaks apart the mess kit. But that doesn't affect the momentum. So the mess kit, because it's an internal force does not affect the total momentum. So the internal forces break apart the mess kit, but do not affect V center of mass or V total. So in other words, V center of mass before the explosion has to be V center of mass after the explosion. Or I could say that the total momentum of the system before must be also the total momentum of the system afterwards. Those are equivalent statements because V center of mass is proportional to the velocity. Now, let's think about this physically here. So physically, what do I know about V center of mass? from the viewpoint of V center of mass, we know that this tells me here is that V center of mass, that this guy is of course a constant, because we saw that there was no external forces. But wait a minute, we also said that these guys had the same mass, but they have different velocities. This is V1, which is moving at 3 meters a second. This is V2, that has a higher velocity. And then, of course, I have my total mass, and my total mass, of course, is M1 plus M2. So what we're seeing here is that this right here, this is telling us that V center of mass line should be closer to V2 than V1. So now let's go draw a nice big picture so that we can actually start to look at this thing. So if I draw this, I could imagine that I have a block moving like this, right? It's moving like this. Here's one. And then I have V2. And I imagine that my V2 is moving like this. So if that's my V2 line, I would expect that my center of mass now should be closer to V2 than to V1. So if I go in and I draw this thing, I could imagine that this is what's happening, that this must be my velocity center of mass line. But this is what happened afterwards. But since it can't change, I can follow this thing back and just say, oh, I had a glob, right? Somebody left this mess kit out. And if they left that out in the sun, what we're seeing here is that this guy should be V center of mass before the explosion. And so when I look at these two things here, now I could then go back and decipher what's actually happening here. And the way I can look at this is that I could look at this in a couple of ways here. And what I'm going to do here is that since we're moving towards momentum, this is the momentum of block 1. This is the momentum of block 2. And this guy is the momentum of the mess kit. And the momentum of these two must be equal to each other. So what we do then is that now that we see what the center of mass is looking like, what we're going to find here is that it's easier to use momentum than V center of mass. So here we go. The total momentum before must be the total momentum after the explosion. So that means this is the momentum of the mess kit. And this has to be the momentum of the green and the red blocks here. But then look what I find here. This guy is in the Y direction. This guy's in the X direction. So now I can write this into component form. So I could write this as M1 V1Y in the J direction. And then this guy's going to be M2 m2 v2x. In the I direction, of course, m2 v2y in the j direction. So I have my momentums now. Note that I can combine that momentum with that momentum. So then if I look at this thing here, since I know that the angle is 30 and it's measured relative to the horizontal axis, I then could come in and write this as m2 v2 cosine of 30 in the I direction. Then I'm going to combine the two j directions, which will give me, look at this, m1 v1, that's only in the j, so that's 90 degrees, so it only has one y component. Then I'm going to get m2 v2 sine of 30 in the j direction. So now, what do I know? Well, I know that m1, m2 is 2 kilograms. We know that v1 has a magnitude of 3 meters per second, and I know that v2 has a magnitude of 5 meters a second. So then I'm just going to substitute these guys in here. So if I put in these numbers, this is what I get. I get 8.66 I plus 11.0 J with units of Newton second. This is the momentum of the system or the mess kit. I now have the momentum. Okay, so I now have the momentum of the system here. So that means I know exactly what happens then. So that means I now know the total momentum of the mess kit, and I could then go in and start to look at a little bit more details, right? So what's the original velocity of the mess kit? Well, I need the magnitude of this guy. Actually, I want to get, so now what I want to do here is that I want
Wait, Carlos,
yeah,
what do you mean by the J and I direction?
because the I is the X direction, the J is the Y direction. So those are the
Okay.
unit vectors.
Oh, okay.
So I'm just decomposing the vector here.
Okay.
Okay. So what is the speed and direction of the mess kit? Well, here's what I know. The mess kit must have had the same direction as V center of mass. Okay. So I know that the total mass of the mess kit must be the mass of the mess kit must be m1 plus m2. So of course that has to be 2 plus 2, which is 4 kilograms. But I also know that the total momentum of the system beforehand does not change, and that should be the momentum of the mess kit. But this guy has to be the total mass of the mess kit plus the center of mass beforehand.
Hey, Carlos, can you rewind real quick? How do we know the total momentum before is equal to the momentum after? Like, how do we know there was no impulse?
Well, because one, it doesn't say anything. They say that the only thing that happened, right? There's no explanation. There's no external forces. Only external forces can change momentum. And what I mean by that is go back to what we did last time, right? If there's no external forces, then the derivative of the total momentum must be 0. So therefore, the total momentum must be a constant, and it can't change. But the total momentum is related to the velocity center of mass. So when I come back to this example then, The only forces that this problem tells us is about the explosion of the mess kit. But the mess kit is part of the system since we isolated the 2 blocks as part of the system. So therefore, since it's internal forces, it doesn't change the velocity of center of mass or the total momentum. Those are 2 of the same statements, and that's what I wrote right here. So then if I come down here, I can't change the momentum of the system, and I can't change the velocity of center of momentum since there's no external forces. So now this allows me then, I could then go in and I can solve for V center of mass of the system. So V center of mass beforehand has to be V center of mass after the explosion. So then it has to be the total momentum. In this case, divided by the total mass of the mess kit. So then if I plug this in, it should be, since this is a vector, I should be careful, right? That's a vector. So now what I need here is that I need the magnitude, right? I need the magnitude of the momentum here. So what we'll do here is we'll say this, the total momentum, since it's a vector, I want its magnitude. So then this should be P final X squared plus P final Y squared. So in this case, it was 8.66 squared plus 11.0 squared square root. And if I calculate this thing, I didn't calculate this thing totally. What I did here is that then I went in and I said this here. V center of mass is then going to be the magnitude of the total momentum divided by the total mass. So in this case, it's going to be 8.66 squared plus 11.0 squared square root. And then the total mass here was 4 kilograms. So then this will give me meters per second. And when I compute this, I get 3.5 meters per second for the magnitude of the center of mass. So now I know what the center of mass velocity is of that. Now, if I go do the exact same thing to get the direction is also the direction of the total momentum. So in other words, this tells me that the direction of the center of mass is also the direction of the total momentum, which then means it should be the tangent inverse of P F final and P F X, which in our case will be tangent inverse of 11.0 over 8.66. And the angle that I get is 52 degrees. And that's what that direction of the center of the mess kit is. It's same as the center of mass. Okay. So now that we have that, we could then go in and start to, I should be a little bit more careful here, because what I'm really doing is that I'm calculating it beforehand. So what angle am I really talking about? Well, if I look at this thing, carefully, what am I seeing here? Well, what I'm seeing here is that picture-wise, let me find my damn mouse. Here it is that this is what I'm seeing. We already agree that this line right here is the velocity of center of mass line. And what we're seeing here is that the momentum of the red particle was smaller. The momentum of the green particle is larger. So then I could imagine that this guy looks something like this here. So what I'd have to do here is that, I don't know if that parallelogram rule is going to match up here, but this is what I know. The angle that I just calculated is this angle, because this is the angle that the mess kit had, right? So we know that the mess kit is coming in this direction. And then after the explosion, it's still coming in this direction. So you could see that the angle that we're really talking about is also this angle too. So, but what we calculated were, it doesn't matter whether I think about it beforehand or afterwards.